you for being here. I'm happy to present my work with Gabriel Scherer, which is a continuation of some projects aiming to improve the OCaml-Rust interface. So this was initially a Nomadic Labs project with Bruno Desfarry and Jacques-Henri Jourdan, and this is a spin-off of that project where we improved the interface of the garbage collector in C, so that we could use it for the Rust interface with OCaml. So why do we want to interface Rust and OCaml? So there is a good synergy between the two languages. Both are strongly typed. They strive for memory safety. Rust is a low-level system programming language. Currently, when people do systems programming in OCaml, they have to mix it with C. And so there is the opportunity to improve the system's narrative around OCaml. There are complementary languages because they are built around different resource management mechanisms. So OCaml has a GC. Rust is very good for managing resources. That is not necessarily memory. So you are building upon the existing OCaml C interface, and we are trying to make it safe in the sense of Rust. So this means that the discipline that the programmers have to follow for the OCaml FFI, we want to express it with the Rust type system. Essentially, this amounts to adding a GC to Rust, and there were earlier works in this area, experiments by Manish Gorigaoka and Alan Jeffrey, who implemented an interface for the JavaScript GC in Rust. On the side of OCaml, there were also experiments to improve the OCaml-Rust interface, the works of Stephen Dolan, Frederic Bourg. I'll talk about it later. First, if we take a step back, I want to propose to see the development of programming languages as trying to mix three layers of concerns. The one is what your program does. Another one is in which abstractions you write those programs. And the last one is which static or even dynamic assurances your programming language gives. In this work, the question is, how can we manipulate OCaml values from Rust? A question of language abstraction. In a way that the OCaml GC discipline is respected and is ensured by the compiler. And lastly, for an FFI, we want competitive performance. So I'll have benchmarks at the end. A few distinctions between the two. So OCaml has a uniform memory representation that allows polymorphism. And so, as we said, the memory is handled with a general GC. Whereas Rust follows the C++ model. So it has a low-level memory representation, which by chance can accommodate the OCaml value representation. It has destructors that are called in a timely fashion. And for these reasons, it is well suited for interoperability. So most of the work is already done by the fact that Rust exists. And the difference between the two memory management methods is that in one, freeing memory is done by traversing the graph of values to find live ones, and freeing memory in the other language is that you traverse a graph to find dead values. So these are the conceptual distinction between the memory management methods. What is the basic idea to implement a GC in Rust in a safe way, to express the discipline of a GC in Rust? So essentially, we want to see this as the same thing as vector allocation, where when you add an element at the end, it can move the vector. And so you can have an iterator invalidation. It means that if you keep a reference to the inside of the vector and you try to use it across an extension of the vector, if you do that in C++, say, it can crash your program or it can do worse things. Rust has a type system that prevents me from doing that. So here is an example of program where I allocate a vector of 3 elements. I get a reference to the first element. I push an element to the vector. This will reallocate the vector. And then declare a second vector. And I try to see what is inside the reference. If I do that in C++, it will print the first element of the second vector, which has no meaning whatsoever related to this the program I have just written. But in Rust, you get an error message that says that you cannot both keep a reference into the vector and try to reallocate it. So it is detecting that there is a possible read which is happening concurrently with a write. So we want to have either a write or several reads, but you cannot mix the two. So the insight of Rust for fixing iterator invalidation, it is a situation a bit similar to data races, and Rust fixes the issues in the same way. So what else moves values? A GC, as I said. So with this analogy, you can understand where how we want to implement a GC in Rust. Instead of a vector, we will pass around a runtime capability that denotes the right to access the heap of OCaml. An iterator is a bit like a pointer into the heap. Inserting an element is like allocating. And now an index for the vector, it's a name which is absolute, which is not does not depend on the location in memory. This will correspond to roots. So root is usually a low-level mechanism, and here we make it a language abstraction. The OCaml C API is callee-roots. It means that when you enter a function, you are responsible for routing all the parameters that are on the stack. This is implemented with a stack allocated linked list. In Rust, there were attempts to do that by Stephen Dolan, and we also tried to do it ourselves. The conclusion is that this can work, but this is complicated and not pleasant to use. The alternative is to pass pointers to values that are already rooted. This is a callee-roots protocol. So the caller is responsible for routing things. This is a bit like the global references in the Java native interface, but our goal is to have a transparent representation that allows us to allocate fewer roots than simply adding roots everywhere. And so in the Rust type system, here how would a signature look like? First, you have to pass the GC capability that denotes the right to access the OCaml heap. And then you can pass references to values. And value ref is a container which is polymorphic in the way the value is routed. If it happens to contain a static value or an immutable value, we can use the Rust type system to relax the conditions so that you don't need to root what does not need to be rooted. So Boxroot is a library that we implemented in C using hooks that are provided by the OCaml runtime. In terms of language abstraction, it presents GCroots as smart pointers, a bit like Rust box. This is where the name comes from. And it when you dereference it, you get a value ref so that you can pass it to functions. In terms of computational behavior, it is a concurrent allocator using standard techniques. In terms of scanning, so it means that you allocate the memory contiguously as possible, and then it's fast to scan for the GC because it's very cache local. We support OCaml-5, and so we have a lock-free deallocation. So in terms of typing, we present a discipline for Rust that heavily relies on Boxroot. More concretely, you manage pools of around 2,000 roots, and you support OCaml-5 by having domain local structures. You allocate in domain local structures. And to be efficient, you need a generational optimization. When you do a minor collection, you want only to scan young roots as much as possible. And I will finish with a few benchmarks. So these are more qualitative benchmarks that helped us understand what was going on in terms of what affects performance. These are very artificial situations. The benchmarks so far are single-threaded, so I am not testing the efficiency of the multi-threaded implementation. And I have 4 implementations. 2 without using roots, and 2 using either Boxroot or some mechanisms that already exist in OCaml. So we compare with existing mechanisms, the global roots and the local roots. We want to be better than both of them. For the global roots benchmark, I do various computations where some OCaml value is stored inside some foreign value is stored inside an OCaml value. And I won't have time to spend too much time in this graph, but the key takeaway here is that it's much faster than the generational roots of OCaml. For local roots, we tested recursive calls, recursive C calls. At every step, we have to root something on the stack. And here we have various implementations. The baseline at the bottom, the black line is not going into C at all. It's a purely OCaml code. And then we see the overhead of the C call plus the routing mechanism. At the top, it's using generational roots, so it's very slow. The second from the bottom is Boxroot using the callee-roots protocol. The blue line below, which is a bit above, is the local roots. So using the callee-roots protocol, we can go faster than the local roots of OCaml. If we do it naively, we get around the same performance as local roots. And finally, the overhead of being thread safe. So we want a single abstraction. We could propose several different versions of roots, but it's not necessary because the most general one is already pretty efficient because the overhead over being thread unsafe is very low. This is the green line below compared to the orange one is the overhead for being thread safe. That's it. The conclusion is that there are practical and academic takeaway from this. So thank you.